Oxford from the inside. The good, the bad, but always the truth.
So we're about to start, and what's going to happen now is if anyone's listening on the podcast, it might be better to watch it as a video on like IGTV or YouTube because Ella's going to ask a maths question, like a typical maths question that might be asked for interviews to Jacob, and he's going to screen share and go through his problem solving. And Jacob's going to ask the question to Ella, and she isn't going to screen share, and she's going to try to answer the question. So we've got an example of a couple of possible maths interview questions, and we've also got a mixed match of different different technology that's available to the students and how they adapt with that. So a bit of a whammy. All right, if you guys want to take it off.
Great, perfect. So my question for Jacob is very nicely phrased, but I will explain it again after. So at the beginning of time, there is a single microorganism, the only member of its species. Each day, it and any future members of its species either split into two copies of themselves or die. If the probability of multiplication is p, what are the chances that the species goes extinct? So the question is, we have a cell, and every day there's a probability p that the cell is going to duplicate, and otherwise it's going to die. So probability of 1 minus p that it dies. We want to know what are the chances that the species goes extinct. So what are the chances that at some point in time there will be no cells left? So
okay, yeah. Okay. I'm hoping you can see like a OneNote notebook that I've screen shared. Yeah. Okay. Nice.
If anyone listening has lost them and needs to restart, that's completely fine because I also lost them. Just to let.
Okay. Yeah. So yeah, maybe yeah. So. A tip that I would like to give here is like if you kind of don't, it's really useful to kind of rephrase the question back to the interviewer, gives you a bit of thinking time and helps you understand the question better. So am I right in thinking like we kind of have like a cell and either one or two things happens, like kind of case one is that the cell dies, which happens with probability 1 minus p, or case two is like the cell splits with probability p. And the question is like, so we have like this population, so maybe we have like a cell, it could split into two cells, and then like this one could die, and then maybe this one could split again into two further cells, and then each of which could die, at which point there's no species left in the population has completely died out. And we're trying to find the probability that this event occurs.
That's it.
Okay, yeah, so my initial approach is like this parameter p is going to be quite important to the question. For example, if like straight away I can see if p is 1, then the probability that the cell dies is 0, and like then the cell would always split. So our probabilities of like extinction is going to be 0 because this is just going to exponentially grow. It's going to double every single time. And then likewise, if the probability of the cell splitting is 0, then the first cell is going to die straight away, and so the probability of extinction is going to be 1. So a sanity check is that those two extreme cases should work. So extreme cases are a good thing to consider. So how might I go about working on this question? Okay, yeah. So I think like I'm going to draw some diagrams and just kind of figure out like a couple of kind of reason through a couple of scenarios, and then hopefully that will lead me to some insight. So. Okay, so let's say the first cell splits with probability p. It's like probability p, the cell splits. And then like these two cells down here, they're like, am I right in thinking these independent copies? Like each cell is independent. Okay, yes. Yeah, that's really helpful. Like independence makes things a lot easier. So now this cell here has like, there are again two scenarios, like there's like probability p that the cell splits into two things, or probability 1 minus p that like this cell dies, which I'm going to represent with red X, maybe not a line. And then same thing for this cell, probability p that we duplicate, probability of 1 minus p that we end here. Okay, so straight away I'm seeing here there's some similarity in like this tree. So maybe like let me kind of reason through what I mean by that. So let me kind of draw a couple of branches of a tree. So each of these dot is a cell, and so maybe here I might like have like time equals 0, time equals 1, time equals 2, etc. And so I think the key thing here is the independence, because that allows me to kind of treat like this tree right here. It's like an identical copy of the main tree here inside itself. So I think this trick is common when evaluating infinite expressions, and that's kind of what I've got here, right? Because like this tree could go on infinitely forever. So I probably don't want to kind of explicitly be computing probabilities. Maybe that would be quite involved, but you could probably do it. So I think I'd like to exploit this symmetry. So I think I'm going to introduce some notation. So maybe let me try and think about what things are important in this situation here. Is like we can have like these layers. So maybe t is important, the time at which we're at, but actually maybe not, because like by the independence here, like kind of time equals 1 is really just 2 copies of time equals 0. So maybe the time isn't really important. Maybe it is. Maybe I can explore that later. I think I'm just gonna kind of go head first. I'm gonna let. I'm gonna consider like the probability the whole thing goes extinct. Okay, so I'm gonna think really about the first node, the first cell. I think that's really important here. The first cell, because everything is very similar to the first cell by its recursive structure. So the probability that this cell goes extinct, like dies instantly. So maybe I should like be clear here about what I'm working out. The probability that the kind of population is 0. Well, I know like this formula that allows me to kind of to split probability up in kind of things in like different situations. So I know like from A level, I have this like the probability of kind of A union B is the kind of probability of A kind of plus the probability of B if kind of like the events A and B are disjoint. Okay, so do I have 2 events here that are disjoint? I think I do. I think I have 2 situations. I think I have like situation 1 is that like this cell dies, and situation 2 is that it multiplies. And I'm sure these events are distinct, like as the cell can't divide and multiply at the same time. So now I can say the probability of the population is equal to 0 is the probability that the population is equal to 0 given that like the first cell dies times the probability that the first cell dies. And then here I can add in the probability that the whole population equals 0 given that the first cell multiplies times the probability that the first cell multiplies. Okay, so what I'm doing here is I think it's called the partition formula. I don't know I think I remember doing something very similar to this at A level, so I hope it's on the specification. But let me just kind of spell that out and be clear to you exactly what I'm using here. Is I'm saying here of like kind of an extension of this. Using the conditional formula for probability, I'm saying the probability of like some event, I'm going to call that E for extinction, is a probability of my event given some scenario where these events A and B are disjoint that I'm using to condition on the probability that the cell dies and the cell multiplies. Is that all sounding okay so far?
This is
Okay,
very much
good.
the right direction.
Okay, that's good. That's thank you for. I think one thing you could always be worried about is if you're going down the completely the wrong path. Okay, so now I know some of this, right? So if like this probability right here, the probability that population 0 is the first cell dies is 1, because if the first cell dies, then that's it. The population is extinct, right? So this is 1, and the probability that the first cell dies, we know from the question is 1 minus p. So this thing here is 1 minus p. I know that the probability the first cell multiplies is p. So the only thing I don't know is the probability that the population is 0 given the first cell multiplies. Okay, so maybe let me explore that. So let's say the first cell multiplies, like let's draw a diagram to kind of visualize what's going on. First cell multiplies, and we have two more cells, and then I'm going to draw it in like green. Maybe this is what happens for the second cell, and maybe in blue, this could be what happens for the third cell, something like this. And then everything dies. And so I think like the idea that like I have these independent copies of like the first node is really important here. So like we know that like these cells are independent. So let me give these cells some names. I'm gonna call this cell alpha and this cell beta. So now in the situation, like this blue probability on line here is really equal to the probability that both like the trees below kind of alpha and beta die. So if both of these kind of trees, like the blue tree and the green tree, kind of stop at some point, like they both get extinct, and then the whole population is dead. So I'm really using that self-similarity here. And so, I mean, what's the probability that like this blue tree dies? Well, by like this independence nature, I think that's exactly the same as the probability that the whole species goes extinct. Because this is a copy of like the population inside itself, like, and by independence, like this nice property of like recursive nature that we have, the probability that like alpha, that the tree below alpha goes extinct is exactly the same as the probability of like the population starting from like this root node is extinct. And the same thing for beta. By symmetry, like that argument exactly holds the same thing. So maybe let me write it down. So the kind of probability. So maybe I should get like it's really important to give things names. I'm going to call like this probability that I want to work out at Q. Oh, it's bad Q. Q. So I'm going to just write capital Q for the probability that the population goes to 0. So the probability that kind of the tree below kind of alpha dies is equal to capital Q. And the same reasoning gives you the probability that the tree below kind of beta dies is equal to Q. Okay. I think I'm kind of getting closer to a solution now. So now like let me kind of take this expression right here and just kind of write out what I know. So I know that Q is equal to, so we have 1 minus P plus P times the probability that we can have trees below alpha and beta die. Is that clear what I mean by like the trees below alpha and beta?
Yes.
Yeah, okay, good,
So.
okay. So now I have like these events that the tree below alpha dies and the tree below beta dies. And I have this formula because I know like these events happening are independent, right? The probability that the tree below alpha dies is independent from the probability that the tree below beta dies because of the fact that these like we have this like self-similar structure going on. I think that's clear. So, and I have this formula for the probability of two things happening. So I know that by independence, I can say this term here is like a probability kind of tree below kind of alpha dies multiplied by the probability that the tree below beta dies. So, and that's q squared. Okay. Oh, nice. Okay. So now I have this quadratic in terms of q, which is what I want to solve. So it's going to be interesting to see, like, my alarm bells are ringing straight away because a quadratic generally has two solutions. So maybe only, it kind of makes sense that maybe only one of these is valid. So that's something that I'm going to watch out for when I solve this quadratic. So I'm going to write it all on like a nice side. I have pq squared minus q plus kind of 1 minus p is equal to 0. Okay, can I factorize this? So if I factorize it, maybe I'm going to have a term that looks like a qp, a term that's like a q equals 0. Well, I know that I need to maybe have something like 1 minus p there. Maybe I need a minus 1. Does that work? Well, I'm going to get a pq squared from expanding those terms out. Then I'm going to get, I hope that works, because I get like this term here is going to give me a minus q, a plus qp. That term there is going to give you a minus qp. That term there is going to give you the minus q. This term here is going to, I think that's a factorization. So now I can solve that so that then q is equal to 1, or q is equal to 1 minus p over p, which equals 1 over p minus 1. Okay, so maybe I have two solutions here. So okay, so maybe I'll give you my answer as 1 minus p minus 1, because it makes sense that this p has something to do with the question.
Okay, so that would be perfect. As a note for people watching the podcast, of course, it's perfectly fine to get stuck, and the tutor will give you input and hints, and that is very much to be expected. Just, Jacob is a third year in those things. All right, so this is nice. So you have two solutions. And sorry, Siam.
Yeah, no, I know if I was answering the question, I would have needed to hint straight away. Actually, I just wanted to ask, would it be like an understandable thing to assume at the beginning that you weren't given enough information? Because I actually thought that, and like that there wasn't enough information to work out what P is. Oh, but I see you haven't worked out what P is, if that's the solution.
Yeah.
Do you see what I mean?
Dependent on P. Yeah, that is a very fair question to ask as well.
So yeah, I think so in this question, if I didn't make that clear, is that P is given to you. So you're not asked to work out P. So like P is like some fixed probability of multiplication. So you're asked to work out a probability of extinction, which depends on P. It's like, so for example, P could be a half, a quarter, a third. You don't know. You just know it's some probability. So the question is not asking you to work out P. It's asking you to work out the extinction, the probability that the species goes extinct. Kind of where P is in the question is probability of multiplication. So I'm sorry if that wasn't clear.
No.
Yeah, I've been trying to kind of explain this and kind of reason this out as I kind of would have done a couple of years ago. So I may have gotten stuck at some points and needed some hints, but I have had a bit of problem solving practice since.
Just a little bit. All right, so this is nice. So now you have two solutions. And these two solutions can't be true at the same time, right? Because then you would need 1 over p minus 1 t equals 0, which can't happen when p is greater than 0.
Oh, wow, yeah, that's a very good point. Okay, yeah, so I need to think about the different scenarios on p. Okay.
Exactly. So now the next question from the tutor might be, or will probably be, so when is the answer q is 1, and when is the answer q is 1 over p minus 1? What are your cases here?
Okay, yeah, that's a very good question. So kind of the first thing I'm going to do is check extreme cases. It's something that I mentioned at the start of the question. So let's like case, I'm writing in red, I don't want to write in red. Let's have like case, kind of extreme case 1 is that like p is 0. Well, then this 1 over p doesn't make sense. So I'm probably going to take q is equal to 1 there. And then the case that then, case 2 might be when p is equal to 1. Well, in that case, then I'm going to have q is equal to 0 from this first solution. or q is equal to 1? Well, if p is equal to 1, then contextually, my species is doubling every single time step. So, and there's no chance of it dying. So my probability of extinction should be 0. So I should want to take this second solution here. So I don't know if I could give these names, like q is equal to 1 minus p minus 1, which in this case for p is equal to 1 would be 0, which makes sense contextually. So then the question is, when do we flip between these two? So I know probability is always between 0 and 1. And so I know that this kind of red underlined expression here, as p approaches 0, this thing is going to get really, really big. So my question is now then is I think I'm going to swap between these two solutions when this red underlined solution gets bigger than 1. So the question is, like, when is 1 minus p minus 1 equal to 1? Well, I can just add 1 to both sides to see that, like, 1 over p is going to be equal to 2. So that happens when p is equal to half. Okay, so I think I'm going to say q is equal to, so 1 over p minus 1 when p is between, so a half and 1. I'm going to say q is equal to 1 when kind of p is greater than, wait, is that right? When less than a half. Wait, is that right? Just that, okay, let me just think. That kind of roughly makes sense. Because like when like this population, when like a cell divides, I'm kind of like I'm getting like 1 additional cell with a probability p. So maybe this is a good extension question that a tutor could ask you, is to kind of like, does this feel right? Like, I think oftentimes in mathematics you can like work out some like really difficult integral, and like, you know, these sanity checks are often really useful. So it's like you work out an integral, it's like a negative number. If the thing you're integrating is positive, that doesn't make sense. So let me kind of try and explain why this makes sense. You know, the tutor would maybe normally ask you and push you in this direction, but maybe let me kind of explain, kind of at least give the listeners or watchers some idea of why this makes sense. So if we have like a cell and it kind of divides, we can think of like how much like the kind of effective weight of like multiplication. So we can have like if you think about like the net count of cells in the population. So then a cell multiplying and dividing into 2 gives the net count a +1 to the population. And a cell dying gives like the net count a -1, right? And then we multiply with probability p, which has weight p, and we subtract 1 with the probability 1 minus p. So it's kind of weight 1 minus p. So for a given cell, they kind of have like this like expected kind of like increase or decrease of the population size for just one cell. And so then if you can take a weighted average of this, so like if I have p, which is +1 times p, then -1 minus p. So here I get 2p minus 1. Okay, and you can see that like this here is going to be greater than 0, say, when p is bigger than a half. And this here is less than 0 when p is less than a half. And it's equal to 0 for p equals a half, right? So what does this kind of mean contextually? Well, it means when p is bigger than a half, like the probability of dividing is kind of is big enough to mean that like the chain, like the population kind of grows on average. And if p is less than a half, then that probability is not big enough to it's not like the chance of reproduction is kind of too small for the chain to kind of grow long term. And you can kind of see that here, right? So q is the probability of extinction, which is guaranteed. The population is guaranteed to go extinct when p is less than a half. And you can see that here, right? When p is less than a half, we kind of expect like cells to be dying. This like expected kind of growth for like one cell is kind of negative. So we expect that the chain is going to decrease. And then when p is like bigger than a half, we kind of expect roughly on average that the population, you know, kind of gets bigger and bigger and bigger But that doesn't mean the population always grows big, and that's why there's still a chance that we might go extinct.
Okay, perfect. That was, so that, the extension of what Jacob was explaining there would be finding the expectation of this distribution, which, if you're interested, is something you could read into as part of the probability course. But another extension question might be, probably quite quick, but a nice one to think about, is just how would you plot P against Q?
Oh yeah, that is quite a standard question. So maybe like this curve here isn't too bad to sketch. I think oftentimes in interviews you'll get asked to sketch things which are a bit more difficult. So maybe if I'm going to sketch the curve, oh no, my pen has just died. That's not good. If I was going to sketch the
so Jacob's
okay,
he's got his pen now. So do you want to resume?
yeah, so I'm gonna quickly sketch the graph. Q is equal to kind of 1 minus P minus 1 when P is between half. I'm gonna sketch the graph of Q against P basically. But I'm just gonna I would kind of walk you through maybe how you might approach a general kind of graph sketch question. So question 1 is key points, like where are the key points on this graph? So we know we're going to have a switch here when P is equal to a half. So I know that like I'm going to put P is equal to a half here. I know that when P is less than a half, Q is 1. Maybe let me just draw this graph first, because I think that's more interesting. So I know that like the graph of 1 over x is going to look something like this. 2 halves, and I'm just going to shift it down 1. So like translation symmetries of graphs is fine. So I know that then, we also know, maybe let me get rid of this here. I also know that then when P is equal to 1, this thing is 0. So if I have P is equal to 1, this thing is going to be 0. And I know it's going to asymptote to minus 1. So here's Q is equal to minus 1. Okay, so then my graph is going to look something like this, and it's going to go to infinity like that. And then I kind of have the same thing on the other side, but shifted down a little bit. So it looks something like that. And then I know that P is equal to a half. I have this cutoff where I go constant. So I know it's something like this. And that's Q is equal to 1 right there. So how I would generally approach a graph sketch question, I think it depends a little bit on the context of the function, but like general things you want to think about are special points, kind of like so consider like, can you sketch bits of the graphs when P is really big, when P is really small? So here you can see when P gets really big, this thing is like minus 1, so you have this asymptote to minus 1. When P approaches 0, we kind of shoot off to infinity. You can kind of consider like turning points of the derivative, kind of symmetry. So is a translation of something you know how to sketch? Can you sketch something similar? Just kind of like break it up into like little bits and kind of maybe join the dots. I think in like in maths or further maths, you sketch rational functions at some point. I think that's a really good exercise. You can get asked to kind of sketch all sorts of wacky things in like maths interviews. And I think a lot of the time it's like you're not expected to get like the exact solution. You just want like the general behavior of the function. But I think that kind of brings us to a nice end for this interview question.
Okay, very nice. That was, by the way, a question from the book called The Riddler by Oliver Roeder, which is really, really good fun. Maybe a bit involved, but they're really nice puzzles if you enjoy that sort of thing.
Is the Riddler like useful for like are there other questions in that book useful for maths interviews?
I'm not sure. I think they get quite involved, and some of the logic ones are nice to think about, but they tend to be a bit too difficult. I think I chose one that was also maybe on the higher end of difficulty, just in terms of content. for A level, but one of the easier ones of the book. So definitely interesting if you end up studying maths maybe in your first year.
Interesting. I thought that was really interesting. I was lost a little bit, so if I wanted to follow, I'd have to go through it slowly. But I'm sure the viewers found that really useful as well, especially seeing how you went through your thought process was really useful as well. I'd imagine, would you both agree though that a typical interview, there would be more of a conversation between the two people? Because normally the students don't know how to do each step straight away.
Yeah, I got a lot of hints, and I said a lot of stupid things. Even in this one, when I was asking the question, I said something stupid at one point. So, like, don't worry about it. And yeah, it'll be a lot slower, and they're always there. Like, at least at Trinity, they're always there to give you hints and help you along. And they want to see what you can do, not watch you struggle.
Yeah, no, exactly. Was there anything else that you both wanted to add before we finish off? Like any advice or anything?
Yeah, so I think we had another interview question planned, which our tutor gave us permission to distribute. But unfortunately, I think we have kind of to run off after this call. So I think I'll leave this as a question for the listeners or watchers to think about. The question is, suppose you have like n greater than 0 distinct lines in the plane, one after another. So none of the lines are parallel to any other, and no 3 lines intersecting at a common point. The plane will then be split into like a number of regions. Call that number capital L subscript n. I want you to find an expression for Ln. Can you find like L1, L2, L3, and can you generalize? Can you find, and maybe as a hint that I would give us to this question is, can you find an expression for Ln in terms of Ln minus 1 and solve it explicitly? Can you indicate L10? Can you think about this for bigger numbers? And then maybe a generalization question that would be like, what happens if you allow like multiple lines to intersect at like a point, and things like that. But I think that one is like on the internet, so maybe that's a good one for you to try out.
Nice, yeah. Well, end it with that. Viewers listening in, try that question at home, and yeah, I hope that that's what we've got time for today. Thank you both for a very interesting podcast, a very useful podcast, for future applicants doing maths. And yeah, thanks for the viewers for listening or watching. If you don't already, follow us on Instagram or Spotify or wherever you find your podcast / YouTube channels. And we'll see you guys next time. Hey guys. Hey guys, we've decided that we are going to do the second question actually. So yeah, I'll leave it to these guys. We're going to do a second maths interviews question, second example of a maths interviews question, and yeah, Jacob, Ella, if you want to take the ball.
Yeah, so this time I'm going to be asking Ella a question. So okay, I'm going to go straight into it. So Ella, we're working in the 2D plane, and you're going to draw n distinct lines in the plane. No 2 of these lines are parallel, and no 3 lines intersect at one point. Okay, and then my question to you is, how many regions will these n lines divide the plane into? So do you have something like can you share a whiteboard, or do you have paper that you can use?
Okay, so I'll share the whiteboard, which will hopefully work. Can you see it?
Okay, great. Yeah.
Perfect.
Okay, so my first question to you is, just so that I know you've understood the question, could you draw some lines in the plane for like, say, n equals 4 that would represent like a possible situation?
Okay, so as far as I've understood, we can just draw any 4 lines, and they're all going to have to cross each other at different points, because you've said that no 2 of them can be parallel, and that no 3 of them intersect at the same point. So if I draw these 4 lines, then this would be a possible example, but they're all going to have to intersect. So if ever 2 lines don't intersect, it'll be because I haven't drawn them out far enough, because in a 2D plane, any 2 non-parallel lines will intersect. so I'll have to be careful when I'm drawing them.
Yeah, that's good. Okay, and then can you just like eyeball how many regions we have here?
Okay, so this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. That would be
Okay,
11
good.
regions. Okay,
So
so
yeah.
how I might go about this problem would be first, if you didn't understand, ask for clarification, obviously. But I think like special cases here were already included in the question. Like if the question had just been how many regions will the plane be divided into by n lines, you could say you would start drawing and quickly realize that if 3 intersect at the same point, then that changes the number of regions. If they're parallel and they don't intersect, that changes. So you'd have to ask about these special cases. But so that's already included in the question, so I think we're good to go. So we would start drawing, just like you asked me to do. And I'd probably start with even a lower case and see if I can spot a pattern in the beginning and if that gets me anywhere. So if I start by maybe keeping tabs and saying how many lines do we have and how many segments is that. So with no lines we have 1 segment, and with 1 line we're going to have 2 segments because I just split it up, 2 segments. That did not work. I go on with it too. A shame. Okay, the text function is maybe not working. We'll go on with it too. I will draw the numbers. Okay, so we had 1 line, 2 segments, no lines, 1 segment. If we have 2 lines, this is going to be split into 4 segments. Okay, so that's looking kind of like a pattern, but what could come next? There could be 8, there could be 7, let's see. If we draw 3 lines, there are going to be 1, 2, 3, 4, 5, 6, 7 segments. Okay, we are starting to see a bit of a pattern. So this is +1. This is +2. Sorry, drawing is odd. Okay, +3. Now we can check and draw another one and see if it works. Actually, we already have right at the beginning when Jacob asked me to draw 4 lines. So we had 4, we got 11, that's +4, it does match. But beyond this, it's going to get quite difficult because like I said before, any 2 non-parallel lines are going to intersect. But because my plane here is quite small, if I start drawing more lines, I'm going to find it hard to draw them long enough that they'll always intersect all the others. So just like before, I had to elongate that line. So if I now draw a line like this, for example, that's okay, it just about intersects, but then maybe a 4th line is going to get difficult in terms of if I want to draw it here, now I haven't drawn it long enough to intersect. I don't know if you can see my mouse to intersect this line, so we're going to have to start actually looking for a pattern, and obviously we want to be able to prove this in the end, so you can't infinitely go on drawing these. So let's think about what's actually happening when I draw a new line, and maybe that will get us somewhere. Let me draw a better diagram, that'll be helpful for this. So say we already have 2 lines, for example. I think this is a nice and easy example to see what's going on. And now we're going to draw a 3rd line. We want to know why that adds 3 extra areas. Well, if I draw a line, like we've said before, it's got to intersect all the other lines because no 2 lines are parallel, and it's got to intersect them at distinct points because no 3 intersect at the same point. So where before there was 1 area, now there are 2. So this here, this was 1 area, and I'll split it into 2. This here, this was 1 area, and now I've split it into 2. And same for this here. That was 1 area, and now I've split it into 2. So I've intersected at 2 points, and I've added 1, 2, 3 different new areas. So let's see if that's making sense. Now if we draw a 4th line, so say we've already got these 3 lines drawn, a 4th line is going to intersect, again, all 3 lines. Above the top line, it's going to split this area into 2 areas now, the middle, this area into 2, this area into 2, this area into 2. So at each point that it intersects, it splits the area above it into 2 areas where before there was 1, and below the very bottom line, the area below it into 2 where there was 1 as well. So in each step we can see, we're always adding n plus 1, and this is this now makes logical sense, the pattern that we've seen. So when there were no lines, we added 1. So to get to the first step, we added 0 plus 1, then we added 1 plus 1, etc. Okay, now we know what this formula is, right? I think this is an A-level, correct me if I'm wrong. What can we write? Let me get rid of these. So if we're looking at n, so we want a formula for how many segments you're going to split the area into with n lines. Then we say here, well, this one was 1, this was 2, so 1 plus 1. This was 1 plus 1 plus 2, right? Because we're always looking at the one before. Okay, this is a bit difficult. 1 plus 1 plus 2. Let's see if this works. Okay, this was 1 plus 1 plus 2 plus 3. 1 plus 1 plus 2 plus 3 plus 4. Well, this is really nice because we know that the sum of the first n numbers is n plus 1 over 2. So now we have that, let's call this an, the nth term of our sequence. So these are the terms, as in the number of lines, and we want the number of areas we're getting from it. That's going to equal the first initial 1, which was the original area I had when there were 0 lines, and then n plus 1 over 2.
Okay, yeah, that's good. Yeah, so that is the correct formula. So congratulations for that. Could you just run me through the general reasoning again? Because you've definitely convinced me for these lower cases. Could you just run me through the reasoning again for a very large number of lines?
Okay, so for a larger number of lines, I think a diagram probably won't help because that's very difficult to draw. But the idea is that at every point of intersection, you've got an area above that point and an area below. Of course, the orientation doesn't really matter, but you've got an area to the left of the original line and an area to the right of the original line that you're now intersecting. So the area to the right, say we're always going to consider the area more to the right or the area more to the right and above. So you can always kind of orient that because any line, if it's going to have an orientation between kind of horizontal and vertical, say we're always looking at kind of this top area here. So however I'm going to orient that, we're always going to look at this side. When I split that with a new line, when I intersect it with a new line, the top area, this side, is going to be split into 2 segments. So we've added 1 area there. Now go along your new line this way. The next line you hit, again, this area on this side, you're going to split into 2 areas, where before there was 1. So if we keep doing that, we're always going to split into 2 areas, where before there was 1. So for each point of intersection, we've added an area. But for the very last point of intersection, we haven't accounted the other side of that line, where there was also an area, because we're looking at the whole 2D plane, so this is going to extend. So where we were below that line, or on, kind of as I was saying before, on this side of that line, we also have to see that there we're splitting where before there was 1 area into 2. So we're adding an extra area. So at each point of intersection, we're adding an area, and then 1 at the very end of our kind of sequence of looking at these. So we're always going to add n plus 1 for n lines for the nth line that we're drawing.
Yeah, that's great. Okay, yeah, thank you. So that was a really nice solution to this first part of the question. So just for listeners, that you could actually come to this conclusion a different number of ways. So I think something that Ella did really well was checking small cases and identifying a pattern just to cement your intuition. I think you should always do that, but you didn't have to spot the formula straight away. You could have solved a recurrence relation to do that. Or you could have also reasoned to this solution thinking about combinatorics, because the number of intersections is very closely related to the number of regions. Okay, so I'm going to ask you now an extension question, which a tutor would kind of maybe like you to push on. So in the first part of the question, we had these kind of quite heavy constraints that no 2 lines are parallel and no 3 lines intersect at a point. So I'm just gonna weaken those a little bit. So now you're going to draw n distinct lines of which no 2 are parallel. But now as many lines as we want can intersect at a point. So as you kind of mentioned earlier, that like depending on how many lines intersect at a point, we get different numbers of regions. So I want to know for n lines, what's the maximum number of regions and what's the minimum number of regions we can split the plane into?
Okay, so following on from my intuition before, I would say that my first instinct would be that whenever we intersect more than 2 lines at a point, that's going to lessen the number of areas that we split into. So to get the maximum number of regions, we want no 2 lines intersecting at the same point. So let's see if we can explain that better. So if we have 2 lines before, every time we intersected, we split into n+1 extra areas. But every time we intersect at one point, now we can treat these 2 lines in effect as like one line, because before I was saying, okay, well, we've got this line and we're going to split. And now the area above and the area below, we're each intersecting into 2 different areas. We're each splitting into 2 different areas, but before there was only one. But now here that we're intersecting at a point, we can kind of say, okay, well, we're only looking at the area above these 2 lines that we're going to split into one, and the area below these 2 lines that we're going to split into one. So in effect, we've reduced the number of areas here that we're going to be able to split. And so whenever you intersect at a point that's already a point of intersection, you have lessened the maximum possible number of areas. So the maximum number of areas, I would say, is where no 2 lines intersect at a point. So that's our solution from before. So oh, I'm still on line drawing. Sorry. Okay, so the maximum of the AM term would be what we had before, 1 plus n plus 1 over 2. Okay. And by the same reasoning, if we always lessen, if we take fewer areas by intersecting a point that's already a point of intersection, my intuition would say that the way to minimize the number of areas would be to always intersect at the same point of intersection. Because now what are we doing? Well, if we keep intersecting at the same point of intersection, then on the nth line, we'll always still just be splitting 2 areas into 2 new areas. So we'll always just be adding 2. And is there a way to do that, to have that number even lower? Because we're asking what the minimum number is, so we need to see, is there any way to go even lower than this? And the answer I think we can pretty easily just intuitively see is no, because if we deviate at all, so I've drawn the slide, see if I can change it, yeah. If we deviate at all from here, if we go this way, now we split into 3 more areas in the middle there. If we go this way, same thing on the other side. And any other orientation, like I said, just any 2 non-parallel lines are going to intersect, and if it's not going to intersect at that one point that all the other ones are already intersecting at, you are then going to get n+1 extra areas like we discussed before. So this is then going to be the smallest number of areas that you can split into. So now we just need to find a formula for that. So let's again, oh, that's a point. Let's again go from base case. So for 0 lines, we have 1 segment. We have that for 1 line, we have 2 segments. For 2 lines, we have 4. For 3 lines, we have 6. For 4 lines, we have 8. And pretty easily, like we said before, you're always adding 2 extra areas. So we're always going to have 2. Oh, I'm still on this. We're always going to have 2 n areas.
Okay, yeah, that's great. So yeah, I think those were the answers that I reasoned to as well. And this also maybe is something to note is that it's like for n=1 and n=2, you have no choice really about how you intersect your lines. And so you can just check that these solutions agree when n=1 and n=2. So the maximum equals the minimum in those cases. So great, yeah, so that's the question solved. So typically in an interview, you might have another question after this, but that was well done.
Thank you. I'm so glad I can in second year finally do interview questions. Quite okay.
So how would you say that example there with Ella, how similar and different that could be to the average interview, or like to your guys' interviews, let's say?
I'd say that the structure of that is about right. You tend to have like the first part of a question, they'll maybe kind of ask you, like I did, to draw like an example to make sure that you've understood the question. But then largely speaking, it'll be left up to the candidate to to reason through kind of the bulk of the question. And then, kind of throughout the tutor might ask you clarification questions or give you hints. And at the end, you're likely to get a follow-on question. I would also say that probably took about the right length of time for an interview question. The interviews tended to be like 20 minutes to half an hour, and you get through 2 or 3 questions in that time, depending on the length of the question.
Nice. And anything to add, Ella?
Yeah, I think, the structure is definitely right. I mean, we did get this question from our tutor, so it is a realistic question. She used it for years. Not anymore. That's why we're using it. And yeah, I guess just in terms of how we answered these questions, it's not realistic at all, I'd say, or at least for me, it really wasn't. Like, I asked a lot of kind of clarifications and I made a lot of stupid mistakes. I was, pretty nervous, pretty tired. And just that's really understandable. And the tutors are there to kind of help you through it. I think the style we did it was very much just kind of having a strong idea of where to go and trying to explain as best as possible so everyone can follow. But yeah, I mean, this isn't kind of the standard that it should be at, which is a good thing to remember. And also interviews are they can be really fun, especially at Trinity, they can be really fun. So that's a nice thing to remember.
No, yeah, especially the chocolate that you get from Melanie.
But also the questions with Melanie were great, honestly. Yeah, and like at the end, Jacob said there's usually like a third question. So the third one was kind of like a brain tease. It was really quick. There were 6 parts, and it was kind of like a logic, like why is this wrong? And it was really fun to do as well. So yeah.
Oh, nice. That's nice to hear. I think it is good to note that I think I know in my interview I asked a lot of questions, and it's quite typical for the candidate to definitely not be too sure about the next step and ask questions. And that's and just similar to most tutorials that we have now at uni, like a back and forth asking questions with the tutor for clarification or to go over things that we don't quite understand, to go and be able to answer the bigger question that they're asking. And I also think something you're saying as well, to add on that, that obviously in this example with you guys, neither of you are stressed, whereas when you're doing the interviews, it can be quite stressful. It might feel like there's a lot hot on the line, and then that very much so yeah, if you feel quite nervous and then you're like, oh, Jacob and Ella seem so calm, I think that is we were definitely probably a lot more stressed at the time. And yeah, if anyone listening and they're about to do the interviews, if they do feel stressed, I know that for me, realizing that the worst case scenario of the interviews wasn't actually that bad at all. Most people applying have 4 top uni offers, options to go to. So I think having that perspective really makes the experience a lot less stressful, and then, as you said, maybe even be able to really enjoy it as you guys did, which is really cool. But I think, sorry, you about to say something? No?
I think also a good thing just to remember for afterwards is don't stress afterwards about how it went and whether you made it, and that can be really nerve-wracking if you're waiting for a month. But I know people who came out of their interviews and got sent home earlier than everyone else and were like, I didn't make it. That's just the way it's going to be, and kind of came to terms with that over the next month, and then made it. And it's just that the tutors thought they did really well and didn't need to see them for more interviews. And I came out of it and I'd had loads of fun, and I thought my last one went okay and it had been a good experience. And then I was terrified because I was like, no, everyone always tells you that if you think it went well, it went awfully, I must have not gotten in. So whatever the experience, you can't read the tutors' minds, and all the tutors are different. So don't stress about it. Try to put it out of your mind and just live life.
No, yeah, for sure. Yeah, there's nothing you can really do about it as well. No matter how much you think about it, you still, just alongside everyone else, you have to wait those 4 weeks. So I definitely agree. If it's possible to not stress about it, I definitely trying to do things that not to think about it, or whatever way you guys deal with stress. But yeah, I think unless you had any words of wisdom, Jacob, for the interviews.
No, I just think if you could, I don't know, sorry. I think just maybe to try and de-stress is I think something they're looking for is a good level of engagement. And I think maybe it takes a minute to get into that, but I think if you really get into the problems and kind of show your flair, that's what they're really after.
Nice. Yeah, for sure. But I think that's all we've got time for today. Thank you both so much for answering these questions and giving us your experiences about the interviews, but also actually doing mock interview questions, because that'd be like so useful for people who have no idea what the interviews are like, to actually see examples. And then the second, as you said before, Ella, the second example question was actually an old interviews question, not one that's being used anymore, hence we're able to use it, but is actually like a question that was used in the interviews for one of the colleges. So which really is really helpful for you guys to go through, because it gives people a really good idea of what to expect. But to the viewers, thanks for listening or watching, whether it's in your podcast or YouTube platforms. And if you don't yet, follow us on Instagram. And we'll see you guys next time.